Welcome to my session. I'm Junzhe Wang from George Mason University. So today, on behalf of my co-authors, Matthew Sharp, Chuxiong Wu, Qiang Zeng, and my advisor, Lannan, I'm happy to present our latest work. In this work, we propose a new direction in binary code analysis called retargeted binary code analysis. Specifically, we want to answer the question, can a deep learning model trained for one architecture be used for others? And nowadays, source code is frequently compiled into binaries of different instruction set architectures, including x86, ARM, MIPS, and PowerPC. Consequently, if the source code contains a vulnerability, then all the binaries generated from the same source code will also inherit the same vulnerability. Therefore, it becomes crucial to thoroughly analyze the binaries for potential vulnerabilities. However, in many cases, we don't have direct access to the source code, making binary analysis even more imperative. However, it is very challenging to analyze binaries in different architectures, because such binaries are very different in terms of their instruction sets, CPU registers, memory addressing modes, and calling conventions. And in recent years, binary analysis tasks have seen promising advancements by incorporating ideas from deep learning techniques. However, there are two challenges for widely adopting deep learning methods for binary analysis across different architectures. And the first challenge is the massive effort to cover multiple ISAs. It requires a lot of data, time, effort, and computing resources to train a deep learning model for each ISA. And the second challenge is the data scarcity problem for some binary analysis tasks with certain ISAs. For example, tasks like malware detection may lack sufficient data sets in some architectures for training an effective deep learning model. And previous research can be broadly categorized into two approaches, the mono-architecture approach and the pairwise architecture approach. In the mono-architecture approach, a model is trained and tested on the same architecture. On the other hand, the pairwise architecture approach, a model is trained and tested for a pair of architectures. And to cover multiple architectures, both approaches need to train a large number of models and collect task-specific data set for each architecture. And in our work, we introduce a solution to tackle the data scarcity problem and handle multiple instruction set architectures more effectively. And we call it Retargeted-Architecture binary code analysis. And our main goal is to achieve model reuse. It means that instead of training a model for each architecture, we want to train only one model for one architecture and then reuse it for other architectures. And specifically, we want to take a model that is originally trained and tested on just one architecture, let's call it mono-architecture, and transform it into a multi-architecture model. And this multi-architecture model can be used on different architectures. And to achieve this, we need to develop innovative techniques that can transfer knowledge from one architecture to others. And in our research, we focus on developing knowledge transfer techniques that enable the reuse of NLP-based models across different ISAs. And to begin our investigation, we want to understand why a model trained on one architecture cannot be used on others. Inspired by NLP-based tasks that use word embedding to capture the contextual meaning, we train the instruction embeddings for 4 architectures, x86, ARM, MIPS, and PowerPC. And then we visualize these embeddings into a 3D spaces. And from the visualization, we can see that the embeddings of different ISAs are separated into different clusters. And this separation is due to the syntactic variation among different instructors. So as a result, a binary analysis model whose input layer encodes each instruction into the instruction embedding trained on one ISA cannot be directly used on others. And given such observation, our goal is to learn a transformation that can map this embedding into a unified space. And this transformation will ensure that similar instructions, regardless of their ISAs, will have close embeddings. We call such instruction embedding as multi-architecture instruction embeddings, or MAIE. And let's take a look at an example of a multi-architecture instruction embedding. So in this visualization, the instructions are represented by different colors, blue for x86, green for PowerPC, and red for ARM. In the initial stage, we select two instructions from x86 and then seek for their similar counterparts from the other architectures. In the mono-architecture embedding, the instructions are clustered based on their architectures. And to group the instruction embedding based on their semantic meaning, we employ a transformation. So after the transformation, we can see that similar instructions, regardless of their ISAs, have close embeddings. And to learn the multi-architecture instruction embedding, we first train the mono-architecture embedding independently for each architecture, and then map them to a shared space through a linear transformation. Let's assume we have X and Y as the mono-architecture embedding matrices of two architectures. And our goal is to map the source X to the target Y. And to achieve this, we aim to find a transformation matrix T that minimizes the sum of the squared Euclidean distances between the mapped embedding XT and the target embeddings Y. And to do that, we first normalize the mono-architecture instruction embeddings to be unit vectors and center on each dimension. And next, we introduce an initial dictionary D, which serves as the initial mapping from X to Y. And finally, we use the initial dictionary D to learn the transformation matrix T, and we use T to induce a new dictionary D, and repeat this process until convergence. For more details of each step, please refer to our paper. So once we have learned the MAIE, our next step is to integrate them into a mono-architecture model. So this integration enables the transformation of a mono-architecture model into a multi-architecture model. We integrate the MAIE to the input layer of the mono-architecture model. And this integration enables the input layer to represent each instruction as its corresponding MAIE. And our evaluation focuses on answering two research questions. First, the quality of MAIE. We aim to determine whether multi-architecture instruction embedding can tolerate the architecture differences and captures instruction semantics across ISAs. Second, the transferability of MAIE. We want to understand whether the knowledge learned from one architecture can be transferred to others. And to access the MAIE, we conduct intrinsic evaluation on the instruction similarity task. To access transferability, we conduct extrinsic evaluation on the malware detection and function similarity detection task. For each task, we train a model on x86 and compute how much the model's accuracy is decreased when tested on different architectures. And due to the time constraints, I will focus on presenting the results of the two extrinsic tasks. To learn the MAIE, we first build a general dataset to train MAIE using C packages, including OpenSSL, binutils, and others. We compile them in 4 optimization levels across 4 architectures, including x86, ARM, MIPS, and PowerPC. In the malware detection task, we first built the task-specific datasets using malware samples across these 4 architectures. And then we built our benign samples from core utils and diff utils. We also make sure that there's no overlap between the general training dataset and the testing sets. We replaced the feature extraction model from the original LSTM model with our multi-architecture instruction embedding layer. And the model trained on x86 can be used to test on not only x86, but also ARM, MIPS, and PowerPC. And our evaluation reveals compelling results. First, when the model is trained and tested on x86, it achieves AUC area under curve of 0.97. When it is reused for ARM, MIPS, and PowerPC, it achieves 0.95, 0.93, and 0.92. And this result shows the good transferability of MAIE. Likewise, in the function similarity detection task, we replace a one-hot embedding layer from the original function model with our multi-architecture instruction embedding layer. And when the model is trained at test on x86, it achieves AUC 0.98. When the model is reused, it achieves 0.95, 0.94, and 0.95 for ARM, MIPS, and PowerPC. In conclusion, we propose a new direction called Retargeted-Architecture binary code analysis. It allows us to reuse a deep learning model trained on one architecture to be used on others, alleviating the per ISA effort and addressing the data scarcity problem. To achieve this, we propose an unsupervised learning method called UniMap, which can learn multi-architecture instruction embedding, where similar instructions, regardless of their architecture, will have close embeddings. And our project will also be open sourced. We are currently working on cleaning up the code, and we plan to upload the source code, trained models, and datasets soon. I will stop my presentation here. Thank you. I'm happy to take questions.